There is a sound, a roar so immense it could shatter worlds, and then nothing, utter silence. This is the paradox of space, a vacuum where the most catastrophic events unfold in perfect, terrifying quiet. Yet just because we cannot hear them does not mean they aren't screaming for our attention across the light years. We gaze up at a seemingly tranquil night sky, a tapestry of peaceful, twinkling lights, but this is a grand illusion. The cosmos is a stage for violence on an almost incomprehensible scale, a continuous fireworks display of creation and destruction where entire suns are born and die in spectacular, explosive finales. What are the most violent, energy-releasing events the universe has to offer? What does true cosmic power look like when it is unleashed without restraint? The answer lies in the fleeting, brilliant, and utterly terrifying moments when the fabric of reality itself is strained to the breaking point. Today, we are embarking on a journey to witness the raw, untamed fury of the cosmos. We will count down the 25 most powerful explosions ever recorded by humanity, a tour of the universe's most extreme phenomena. These are not mere chemical fires or simple bursts of light. These are events where a single star can, for a few weeks, outshine its entire host galaxy, where the death throes of a massive sun forge the very elements that make up our bodies and our world. We will travel from the shockwaves of supernova that ripple through stellar nurseries to the mysterious, hyper-energetic flashes known as gamma-ray bursts, events so luminous they are visible from the far side of the observable universe. We will even confront detonations on a galactic scale, where supermassive black holes unleash jets of energy that can sterilize entire swaths of space. This is a story written in light, radiation, and raw force, a testament to the fact that the universe is far from a peaceful place. Our ability to witness these events is a triumph of human curiosity and technology. For most of human history, these celestial cataclysms occurred unseen, their light traveling for millions or even billions of years only to fade without a witness. But now, with powerful telescopes orbiting our planet and sophisticated instruments scanning the heavens, we can finally see the universe for what it truly is, a dynamic, often violent, and always breathtaking arena. This video is your front row seat to the greatest show the cosmos has to offer. So prepare to be humbled, to have your perspective shifted, and to feel a sense of awe that only the grandest scales of time and space can provide. The countdown of the most powerful explosions ever recorded begins now. And we begin our countdown not with a distant, ancient event, but with a ticking time bomb in our own cosmic backyard. At number 25, we find a star that staged such a violent, dramatic outburst in the 19th century that it temporarily became the second brightest point of light in the entire night sky, surpassed only by Sirius. This is Eta Carinae, a monstrous, unstable stellar system located about 7,500 light-years away. What astronomers witnessed back in the 1840s wasn't a final, death-dealing supernova, but something perhaps even more bizarre, a supernova impostor event. In a cataclysmic tantrum, Eta Carinae did not simply explode and fade away. Instead, it underwent a colossal eruption, violently ejecting an almost unimaginable amount of its own mass into space. We're talking about more than 10 times the mass of our own sun being thrown out in a titanic stellar wind. To put that into perspective, that's the equivalent of hurling the entire solar system, minus the sun itself, out into the void. The most fascinating part of this entire story is that the star survived. It didn't tear itself completely apart. This eruption was a partial, contained detonation, a warning shot across the bow of our galaxy. The evidence of this violent episode is now beautifully encased in the Homunculus Nebula, a vast, dumbbell-shaped cloud of dust and gas that expands outward from the central star. This nebula is a perfect three-dimensional time capsule of that 19th century explosion. we can literally see the debris field from the event still moving outward at tremendous speeds. At the heart of this beautiful chaos sits Eta Carinae itself, a binary system where the primary star is a behemoth, estimated to be around 100 times the mass of our Sun. It's a star living on the edge, so massive and luminous that the outward pressure of its own radiation barely counteracts the immense inward pull of its gravity. This makes it profoundly unstable, perpetually on the verge of tearing itself to pieces. And that brings us to the future. Eta Carinae is a prime candidate to end its life in a spectacular supernova, and in cosmic terms, it could happen at any moment tomorrow or in 100,000 years. When it finally does go, it won't be a subtle event. A supernova from Eta Carinae would be a celestial spectacle unlike any seen in recorded human history. It would shine with the intensity of a full moon, becoming easily visible in the daytime sky for weeks on end, casting shadows at night and potentially even being bright enough to read by. It would be a magnificent, terrifying, and humbling reminder of the raw power that dwells within the heart of a star. For now, Eta Carinae and its homunculus nebula stand as a stunning monument to a past eruption and a stark preview of an even greater explosion yet to come. If Eta Carinae represents a future cataclysm waiting in the wings, then the event we arrive at now showcases a detonation so brilliant it fundamentally rewrote our understanding of what is physically possible in a stellar explosion. Securing the number 24 spot is the record-shattering supernova known as SN 2015L, or by its more technical designation, Assassin 15LH. Discovered in June of 2015 by a network of automated telescopes specifically designed to scan the skies for such transient events, this was no ordinary star death. When its light finally reached us from a galaxy 3.8 billion light-years away, the data it carried was nothing short of astronomical. At its peak brilliance, this single exploding star achieved a luminosity calculated to be 570 billion times brighter than our own Sun. To even begin to comprehend that number, try to picture this. For a brief, glorious moment, this one object radiated more light than every single star in the entire Milky Way galaxy combined. It wasn't just a new record, it was an event that pushed the very limits of our physical models, belonging to an ultra-rare class known as superluminous supernova. The sheer intensity of this flash immediately presented a profound mystery to astrophysicists. What conceivable engine could possibly generate that much energy? A typical supernova, the kind that marks the death of a massive star, simply doesn't have the power. The leading hypothesis initially pointed towards an incredibly exotic and dense object, a magnetar. Imagine the core of a dead star collapsing not into a standard neutron star, but into something far more ferocious, a rapidly spinning neutron star possessing a magnetic field trillions of times stronger than Earth. This celestial dynamo, spinning at hundreds of times per second, would transfer its immense rotational energy into the expanding shell of debris from the explosion, essentially acting like a cosmic blowtorch to brighten the aftermath to unprecedented levels. It was a beautiful, elegant theory that seemed to fit, requiring a perfect storm of conditions. A star of just the right mass collapsing into a core of just the right density, spinning at just the right speed. However, as more data streamed in over the following year, the plot thickened considerably. Observations from the Hubble Space Telescope revealed that the host galaxy of this supernova was an exceptionally massive and quiescent one, the exact kind of place where you would expect to find a supermassive black hole at its center, not the kind of bustling stellar nursery where massive, short-lived stars typically form and explode. This puzzling detail gave rise to an even more dramatic and frankly terrifying alternative explanation. Perhaps this wasn't a supernova at all in the traditional sense. What if we were witnessing the tidal disruption of a star? In this scenario, a star similar to our own Sun wandered too close to the supermassive black hole at the heart of its galaxy. The incredible tidal forces, the difference in gravity between the side of the star nearest the black hole and the side farthest away, would have stretched and compressed the star, literally pulling it apart into a long, thin stream of incandescent gas. This stellar material would then spiral into an accretion disk around the black hole, heating to millions of degrees and unleashing a final, brilliant flare of light as it was consumed. This event would mimic the signature of a supernova, but its power source would be purely gravitational, a direct feast from a cosmic predator. The ongoing debate surrounding Assassin 15LH is in many ways more valuable than a definitive answer. It highlights a critical and exciting frontier in modern astronomy. We are now discovering events that do not neatly fit into our existing catalogues, phenomena that challenge us to invent new physics or to apply known processes in radically new contexts. Whether it was the spin down of a newborn magnetar or the shredding of a star by a black hole, this explosion demonstrated that the universe possesses methods for unleashing energy that we are only just beginning to catalogue. It serves as a powerful reminder that for every rule we establish about how stars live and die, the cosmos is ready to present an exception that is far more brilliant and far more mysterious than we ever thought possible. Leaving behind the staggering scales of superluminous supernova, our journey takes a sharp turn toward the truly bizarre, arriving at an explosion so peculiar it earned a name that stands out from the usual alphanumeric designations. At number 23, we encounter the cosmic mystery officially known as a 2018 cow, an event that captivated and confused astronomers in equal measure. Discovered in June of 2018 by a survey in Hawaii, its automated designation used the last 3 letters of its unique identifier cow, and the name, almost comically mundane, stuck. But there was nothing ordinary about what this object did. It appeared seemingly out of nowhere in a galaxy 200 million light-years away, and it did not behave like any supernova ever seen before. Its rise to peak brightness was astonishingly rapid, achieving incredible luminosity in just a matter of days, not weeks. Simultaneously, it was unbelievably hot, shining with an intense, brilliant blue-white light and emitting a tremendous amount of energy in X-rays and radio waves. This was not the slow, reddening fade of a typical stellar explosion. This was a flash of something entirely different, something much faster and far more energetic in its early phases. The peculiarities only deepened with closer observation. Typically, a supernova's expanding shell of debris creates a thick, opaque curtain that hides the inner engine of the explosion for some time. But with the cow, that curtain seemed to be missing. Astronomers could essentially see right into its heart, observing the central power source directly, which was phenomenally hot and remarkably small. This transparency was a crucial clue, suggesting the ejected material was much less massive and much faster moving than in a standard supernova. It was as if a star had experienced a violent hiccup, blowing off a relatively thin outer layer at incredible speed, rather than a full-scale self-destruction. This strange combination of characteristics, the rapid brightness rise, the extreme heat, the unusual transparency, and the powerful high-energy emission, immediately sparked a fierce debate within the astrophysics community about what exactly they were witnessing. Several compelling, exotic theories emerged to explain the cow's bizarre behavior. One leading idea proposed this was a failed supernova, also known as a core collapse supernova that didn't quite succeed. In this scenario, the core of a massive star collapses directly into a black hole. Instead of a shockwave rebounding to blow the star apart, most of the stellar material falls inward, but a small amount of matter is ejected in fast-moving jets at nearly the speed of light. This would account for the cow's high velocity, its unusual brightness in X-rays, and the fact that we could see so deep into the event so quickly. Another hypothesis suggested we were seeing a tidal disruption event where a white dwarf star was ripped apart by an intermediate mass black hole. The shredded stellar material swirling down into the black hole's maw would create an intensely hot accretion disk and produce the brilliant, fast-lived flash that was observed. Yet a third possibility was that this was a special type of core collapse supernova, one where the collapsing star had previously stripped away its outer hydrogen envelope, leaving behind a much more compact and hot object whose explosion we could witness in unprecedented detail. The true legacy of the cow, however, extends far beyond solving the puzzle of this single event. Its discovery effectively announced the existence of an entirely new class of cosmic explosions, now known as fast blue optical transients, or FBOT. These are the universe's flashbulbs, incredibly luminous, incredibly fast, and incredibly hot events that appear and vanish on timescales that make even regular supernova seem slow and lumbering. The cow was the first of its kind to be studied in such exquisite detail with the full power of modern observatories, from radio telescopes on the ground to X-ray satellites in space. It served as the prototype, the Rosetta Stone for understanding this new category of astrophysical phenomena. It taught astronomers that the menagerie of stellar deaths is far more diverse and strange than we had previously imagined, revealing a hidden zoo of explosive events that had been occurring all around us, largely unnoticed because they come and go so quickly. The cow didn't just provide an answer, it fundamentally opened up a new set of questions, proving that even in an ancient universe, there are still entirely new kinds of fireworks waiting to be discovered. From the fleeting brilliance of the cow, we journey to an event that wasn't just seen but felt. An event that literally shook the fabric of space-time itself and ushered in a new era of cosmic observation. Claiming the number 22 spot is an explosion so significant it carries two names: the gravitational wave event GW170817 and the corresponding kilonova known as at 2017 GFO. On August 17, 2017, for the very first time in human history, we didn't just watch a cosmic catastrophe from a distance, we experienced it with multiple senses in a way. The twin detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, along with the Virgo detector in Europe, registered a distinctive ripple in spacetime that lasted for about 100 seconds. This wasn't the chirp of two black holes merging which had been detected before. This signal was different, richer, and it was immediately followed by a gamma-ray burst detected by the Fermi and Integral Space telescopes just 2 seconds later. The gravitational waves told us that two incredibly dense objects had just spiraled into each other, and the gamma-ray flash confirmed a violent explosion. The race was on to find the light, and find it they did, thanks to the precise sky localization provided by the 3 gravitational wave observatories. Astronomers around the world pointed their telescopes at a patch of sky in the constellation Hydra. There, in a galaxy known as NGC 4993, about 130 million light-years away, they found a new, bright pinprick of light that hadn't been there the night before. This was the Kilonova, the visible aftermath of the neutron star collision. As the two ultra-dense corpses, each more massive than our Sun, yet only about the size of a city, smashed together, they shredded each other apart in a cataclysm of unbelievable violence. The collision ejected a vast cloud of hot, neutron-rich debris expanding at a significant fraction of the speed of light. Within this cosmic cauldron, a rapid series of nuclear reactions, known as the Rapid Neutron Capture Process or the R process, took place. This is the primary cosmic forge for the heaviest elements in the universe. In a matter of seconds, this single event produced a staggering amount of platinum, gold, and other rare elements. The calculations are breathtaking. It's estimated that the explosion created gold with a mass several times that of our entire planet, and platinum many times over. The wedding ring on your finger, the gold in a microprocessor, the platinum in a catalytic converter. The seeds of all these elements were cast into the universe in events exactly like this one. This event, GW170817, marked the triumphant birth of multi-messenger astronomy. For the first time, we could correlate the feel of gravitational waves with the sight of electromagnetic radiation across the entire spectrum: gamma rays, X-rays, visible light, and radio waves. Each messenger brought a different piece of the story. The gravitational waves revealed the masses of the neutron stars and the dynamics of their final, dying orbits. The initial gamma-ray burst confirmed the presence of powerful jets launched by the merger. The visible light of the Kilonova, which glowed a brilliant blue and then faded to a deep red over several days, gave us a direct signature of the heavy elements being synthesized and ejected. It was like hearing the crash of a cymbal, seeing the flash of a light, and smelling the smoke all at once, allowing us to reconstruct the entire event in unprecedented detail. Beyond confirming the origin of heavy elements, this collision provided profound insights into the nature of matter itself. Neutron stars are essentially giant atomic nuclei, and their interiors remain one of the greatest mysteries in physics. What happens to matter compressed to densities so extreme that a single teaspoonful would weigh billions of tons? Does it become a soup of free quarks or a superfluid of exotic particles? The observations from this merger placed new, stringent limits on the possible states of this ultra-dense matter, informing theories that were previously untestable. Furthermore, the event helped resolve a long-standing debate about the origin of short gamma-ray bursts, conclusively linking them to binary neutron star mergers. The aftermath of the collision also left a lingering mystery. What was the final remnant? Did the merged object immediately collapse into a black hole, or did it briefly form a supermassive neutron star before its ultimate demise? The data continues to be analyzed, but the legacy is already secure. GW170817 was a watershed moment, a single event that connected the physics of the very small to the cosmos at large, proving that the universe's most powerful explosions are not just agents of destruction, but also the fundamental creators of the world we know. But now, we turn our attention from the deaths of stars to the engines at the very heart of galaxies, where a different kind of power is on display, one that is not a fleeting blast, but a continuous, seething eruption on a scale that dwarfs even the most brilliant supernova. Securing the number 5 spot isn't a single, momentary detonation. It is an ongoing, colossal outburst from the supermassive black hole at the core of the galaxy Messier 87. This is the monster in M87, a gravitational behemoth weighing in at a staggering 6.5 billion times the mass of our Sun, and it is famous not just for being the first black hole ever directly imaged by the Event Horizon Telescope, but for the titanic jet of matter it fires into the cosmos. This jet is a persistent explosion, a focused beam of subatomic particles and radiation screaming out from the galactic core at over 99% the speed of light, stretching for thousands of light years into the intergalactic void. It is a testament to a form of energy release that is both more controlled and more devastatingly powerful than any stellar death. So, how does a black hole, an object famous for its gravity being so strong that not even light can escape, become the source of such an immense outward-flowing jet? The secret doesn't lie within the event horizon itself, but in the frenzied, chaotic maelstrom just outside it, the accretion disk. Imagine a vast whirlpool of gas, dust, and shredded stars, all spiraling inward at velocities approaching light speed. As this material falls toward the point of no return, it is compressed and heated to millions of degrees, causing it to glow with intense radiation across the entire electromagnetic spectrum. But the true particle accelerator is born from the interplay of this superheated plasma with the black hole's own incredible rotation and its powerfully twisted magnetic fields. These magnetic field lines act like the rigid rails of a colossal slingshot, channeling a fraction of the infalling material and flinging it away from the poles of the black hole, not inward. This process transforms the black hole's immediate environment from a simple drain into a powerful engine, capable of launching focused jets that punch clear through the surrounding galaxy. The energy output of this continuous eruption is almost beyond human comprehension. The jet from M87's black hole pumps out energy equivalent to the rest of the entire galaxy combined, and it has been doing so for millions of years. This is not a brief flash in the pan, it is a relentless, eons-long torrent of power. The particles within the jet, accelerated to such phenomenal speeds, emit a brilliant synchrotron radiation, a telltale glow that we can detect from radio waves to X-rays. This makes the jet from M87 a lighthouse beacon in the universe, visible across vast cosmic distances and serving as a perfect laboratory for studying the most extreme physics imaginable. But these jets are far more than just spectacular cosmic light shows. They are galactic-scale regulators with the power to shape the evolution of entire galaxies. When a jet like the one in M87 plows through the interstellar medium, the vast clouds of gas and dust that are the raw material for new stars, it does so with unimaginable force. It can heat the surrounding gas to such high temperatures that it can no longer collapse under its own gravity to form new stars. In more violent interactions, the jet can physically blow the gas clear out of the galaxy, stripping it of its future stellar fuel. This process, known as quenching, effectively shuts down star formation, dooming a galaxy to a gradual, passive aging process. The supermassive black hole, through the explosive power of its jets, acts as a cosmic thermostat, preventing the galaxy from becoming too massive and self-regulating its own growth. The brilliant, destructive jet erupting from the darkness of M87 is therefore not merely an explosion. It is a fundamental force of cosmic construction and destruction, a permanent fixture in the universe's arsenal of power that governs the very life and death of galaxies. Moving from the continuous fury of galactic jets, we encounter a stellar explosion so uniquely brilliant and prolonged that it stands as a landmark event in modern astronomy. Capturing the number 6 position is the extraordinary supernova known as SN 2006 Gi. In September 2006, a star in the distant galaxy NGC 1260, located about 240 million light-years away, ended its life in a fashion that defied all conventional expectations. While a normal supernova might briefly rival the brightness of its host galaxy before fading over weeks or months, SN 2006 Gi was in a class of its own. It took nearly 3 weeks just to reach its dazzling peak, and when it did, it achieved a luminosity that was staggering. At its brightest, it shone with the intensity of 50 billion suns, outshining its entire host galaxy for months on end. The total energy released was hundreds of times greater than that of a typical core collapse supernova, demanding a completely different kind of explosive mechanism to explain its sheer power and staying power. The leading theory that emerged to explain this cataclysm is as fascinating as it is violent: the pair instability supernova. This rare event can only occur in the most massive stars the universe can produce, behemoths with estimated initial masses between 130 and 250 times that of our Sun. Within the core of such a monster star, temperatures and pressures reach such unimaginable extremes that the radiation trapped inside is fundamentally changed. The photons of light, which normally provide an outward pressure that supports the star against its own immense gravity, become so energetic that they spontaneously transform into pairs of particles and antiparticles, specifically electrons and positrons. This transformation is catastrophic. In an instant, the outward radiation pressure that was holding the star up suddenly vanishes from the core. Without this support, gravity wins an instantaneous and total victory. The star's core collapses violently inward, but this is not the quiet collapse into a black hole that we might expect. As the core implodes, it heats up to even more unbelievable temperatures, eventually triggering a runaway thermonuclear explosion that does not simply blow off the star's outer layers. It utterly and completely annihilates the entire star. In a runaway fusion frenzy, the star's core fuses oxygen and heavier elements in an unstoppable chain reaction. There is no remnant left behind, no neutron star, no black hole. The entire stellar structure is disassembled in one of the most powerful thermonuclear events possible in the universe, scattering its enriched guts across interstellar space. SN 2006 Jai is one of the strongest real-world candidates we have for such an event, a cosmic testament to a star so massive that it was ultimately destroyed by the very nature of light and matter within its own heart. The significance of SN 2006 Jai extends far beyond a single, spectacular stellar death in a distant galaxy. It provides us with a rare and precious window into the universe's earliest chapters. The first stars to form after the Big Bang, known as population 3 stars, are theorized to have been these kinds of colossal, pristine giants composed only of hydrogen and helium. With no heavier elements to cool them down, they could grow to tremendous sizes, many likely residing in the mass range required for a pair instability supernova. Therefore, witnessing an event like SN 2006 Jai in a relatively nearby galaxy is like catching a glimpse of the death of one of the universe's first stars. It validates a long-held theory about how the earliest stellar behemoths lived and died, and it shows us the kind of explosive nucleosynthesis that must have seeded the primitive cosmos with the first heavy elements, paving the way for the eventual formation of rocky planets and ultimately life itself. This single explosion connects our modern, element-rich universe directly to its violent and magnificent origins. Just when we thought we had mapped the most extreme corners of the cosmic explosive spectrum, the universe revealed a phenomenon so brief and so powerful it defied all conventional explanation for years. Claiming the number 7 spot is not a single, isolated blast, but a mysterious, repeating signal from the depths of space, the fast radio burst known as FRB 121102. Discovered in 2012 in archived data from the Arecibo Radio Telescope, this event, and others like it, presented a profound puzzle. A fast radio burst is exactly what its name implies, a flash of radio waves that arrives from deep space, lasting only a few thousandths of a second. But within that sliver of time, it unleashes a staggering amount of energy equivalent to the total output of our sun over several decades. Imagine the entire energetic lifetime of a star compressed into a blink of an eye. That is the raw, concentrated power of an FRB. For the first few years after their discovery, all known fast radio bursts were one-off events. They would flash once from a random point in the sky and then vanish forever, leaving astronomers to theorize they were caused by ultimate, catastrophic one-time events. Perhaps they were the final death cries of stars being vaporized by black holes, or the colossal mergers of ultra-dense objects like neutron stars. The one-and-done nature pointed to a source that was destroyed in the process. That is, until FRB 121102 did the unthinkable. It repeated. In 2016, astronomers confirmed that this specific source was flashing again and again, sending out multiple bursts from the same location. This single observation immediately overturned the leading cataclysmic models. You cannot have a star explode multiple times. The repeater had to be powered by an engine that could survive its own outburst, an object capable of producing multiple universe-shaking hiccups without tearing itself apart. The search for the source of these repeating bursts led to a surprising and revealing location. Precise radio telescope observations traced FRB 121102 back to a tiny, faint dwarf galaxy more than 3 billion light-years away. This was a crucial clue. This wasn't a large, stately spiral galaxy like our Milky Way, but a small, unassuming cosmic backwater that was actively forming new stars. Such dwarf galaxies are often rich in the kind of raw, primordial gas that serves as the building blocks for massive, short-lived stars. This environment strongly hinted that the source was a young object, the remnant of a recent, violent stellar death. The most compelling candidate that emerged from this evidence is one of the most extreme objects known to astrophysics, a magnetar. A magnetar is a type of neutron star, the collapsed core of a massive star that went supernova, but it possesses a magnetic field that is 1,000 trillion times more powerful than Earth. To put that almost incomprehensible strength into perspective, a magnetar located halfway between Earth and the Moon could wipe the data from every credit card on our planet. The leading theory suggests that these repeating FRBs are produced by colossal starquakes on the surface of a young, hyperactive magnetar. Picture this object, a city-sized ball of ultra-dense matter, spinning rapidly and encased in an unimaginably powerful magnetic field. This magnetic field is so strong that it actually stresses and twists the solid crust of the neutron star itself. Occasionally, this crust can fracture in a starquake that releases more energy than 1,000,000 magnitude 10 earthquakes. These quakes violently shake the magnetar's magnetic field, which in turn accelerates particles to near light speed, generating an intense, focused beam of radio waves that shoots out across the cosmos. If that beam happens to sweep across our line of sight for those few precious milliseconds, we detect it as a fast radio burst. The repeating nature of FRB 121102 suggests its magnetar is in a particularly volatile youth with a dynamic environment that allows for these frequent energetic fractures. The discovery and continued study of this repeating burst fundamentally transformed our understanding of these enigmatic signals. It proved that the population of FRBs is diverse, with some being one-off cataclysms and others being persistent, repeating engines. This opened up an entire new field of time-domain astronomy, where scientists can now study the same FRB source repeatedly, watching how its properties change over time and using it as a unique laboratory to probe the most extreme states of matter. Furthermore, the incredible energy and brevity of these bursts make them powerful tools for cosmology. As the radio waves travel across billions of light years, they pass through diffuse clouds of ionized gas and are subtly dispersed. By measuring this dispersion, astronomers can effectively weigh the invisible matter between galaxies, mapping out the cosmic web that constitutes the large-scale structure of our universe. The brief, brilliant flash of a repeater like FRB 121102 is far more than a cosmic curiosity. It is a precision tool, a messenger from a uniquely violent environment, and a humbling reminder that some of the universe's most powerful explosions are not grand, lingering fireballs, but ultra-fast pulses of pure power echoing across the cosmos. But what if the most terrifying explosion isn't one we observe from a safe distance in a far-off galaxy, but one that occurred right here in our own cosmic home, and we are living in its quiet aftermath? This brings us to number 8 on our countdown, an event that reshaped our very own Milky Way, the great outburst from our galaxy's central supermassive black hole, Sagittarius, a star. For decades, we considered our galactic center to be a relatively peaceful place. Sagittarius, a star, while possessing the mass of 4 million suns, has been a quiet, sleeping giant during all of human history, emitting only a faint whisper of the energy it is capable of producing. But mounting evidence now reveals a dramatic and violent past. Our galaxy was not always this calm. Millions of years ago, it was a powerful quasar, and the echoes of that ferocious awakening are still visible today, etched across the sky in a pair of colossal structures known as the Fermi bubbles. Discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope, the Fermi bubbles are perhaps the most striking fossil evidence of this ancient cataclysm. These are not small features. Imagine two vast orbs, one extending tens of thousands of light years above the galactic plane, and another, identical in size, stretching an equal distance below it. Together, they form a gigantic, hourglass-shaped structure that encompasses the entire central core of the Milky Way, a cosmic monument to a long-ago eruption. They are not visible in ordinary light. Instead, they glow with the high-energy signature of gamma rays produced by ultra-fast cosmic rays interacting with the thin gas that permeates intergalactic space. These bubbles are essentially the scorch marks, the blast zone, from a titanic bipolar jet that once screamed out from Sagittarius, a star. The energy required to inflate such immense structures is staggering, equivalent to the simultaneous explosion of perhaps 100,000 supernova. This was not a single, quick blast, but a sustained eruption that likely raged for tens of thousands of years, a fiery breath from the dragon at the heart of our galaxy. So, what could possibly have stirred our sleeping giant from its slumber and triggered such a violent awakening? The most probable culprit is a sudden and enormous feast. Supermassive black holes like Sagittarius, a star, are powered by their accretion disks, the swirling pools of gas and dust that spiral inward. For most of its recent life, our black hole has been on a strict diet with very little material falling in. But in the past, a vast cloud of gas, or perhaps even an entire star cluster, may have wandered too close to the galactic center. The immense gravitational tides would have torn this structure apart, funneling a colossal amount of raw fuel directly into the black hole's waiting maw. As this material was compressed and heated to millions of degrees in the frantic whirl of the accretion disk, it would have begun to glow with unimaginable brilliance, transforming Sagittarius, a star, from a dim ember into a brilliant quasar. The physics of such a well-fed black hole almost inevitably leads to the formation of powerful jets. As we saw with M87, the intense magnetic fields and rapid rotation can channel some of the infalling material into two focused beams, shooting out from the black hole's poles at nearly the speed of light. It was these very jets pumping unimaginable energy into the galactic halo that painstakingly carved out and inflated the enormous Fermi bubbles we observe today. The consequences of this eruption for the galactic environment would have been profound. Any star-forming regions or nascent planetary systems lying along the path of those jets would have been subjected to an unimaginable onslaught of radiation and particles. The intense flood of energy would have sterilized vast tracts of space, stripping away atmospheres and scouring the surfaces of worlds. Conversely, the shock waves from the expanding bubbles may have also played a constructive role, compressing distant clouds of gas and triggering a wave of new star formation in their wake, a paradoxical cycle of destruction and creation. For any hypothetical life forms existing in the Milky Way at that time, the awakening of the core would have been a celestial event of terrifying magnitude. The central bulge of our galaxy, which now appears as a softly glowing band of starlight, would have blazed with the light of 100 million stars, potentially outshining the full moon and casting shadows on planets tens of thousands of light years away. We are living in the long, quiet peace that followed that storm, a testament to the fact that even our own familiar, seemingly stable galaxy has a volatile and explosive history written into its very fabric. Now we arrive at one of the most energetic and conceptually elegant explosions in the cosmos, a two-part cataclysm that links the death of a star directly to the most luminous electromagnetic events known. At number 9, we explore the hypernova and its telltale beacon, the long-duration gamma-ray burst, exemplified by the spectacular GRB 130427A. Detected in April 2013, this event was a landmark in modern astrophysics. It was both extraordinarily bright and relatively close, a mere 3.6 billion light-years away, which in cosmological terms is practically in our backyard. For about 20 seconds, this single object flooded space telescopes with high-energy gamma radiation, becoming at its peak the brightest source of gamma rays ever observed in its energy range. But this brilliant flash was only the opening act, the first desperate signal from a star undergoing an unimaginably violent transformation. The story of a long gamma-ray burst begins not with the explosion itself, but with the unique life of the star that fuels it. This isn't just any massive star, it's a Wolf-Rayet star, a colossal, rapidly spinning beast that has already shed its outer layers of hydrogen through powerful stellar winds, leaving behind a bare, blazing hot core of helium and heavier elements. This rapid rotation is the key ingredient. When such a star finally exhausts its nuclear fuel, its iron core can no longer support its own weight and collapses catastrophically, not into a neutron star but directly into a black hole. Because the star is spinning so fast, the infalling material doesn't just plummet straight in. It forms a vast, incredibly hot and dense accretion disk around the newborn black hole, a maelstrom of matter spiraling into oblivion. It is from this cosmic vortex that the true power is unleashed. The immense gravitational energy released by this feeding frenzy, combined with the star's rapid rotation, acts as a powerful engine. It funnels a fraction of the inflowing material into two narrow, counter-flowing jets that blast outward from the star's poles at velocities exceeding 99.9% of the speed of light. These are not gentle streams, they are ultra-relativistic blowtorches, focused beams of pure energy. The jet is so narrow and concentrated that if you were to view it head-on, its brilliance would be unparalleled. For GRB 130427A, one of those jets was pointed almost directly at Earth. We were looking right down the barrel of the universe's most powerful cannon. The gamma-ray burst we detected was the jet punching its way through the outer layers of the star itself, a burst of intense radiation generated by internal shocks and collisions within the jet as it fought its way to freedom. But what happened after the initial flash confirmed a long-held theory. The collapsar model for long gamma-ray bursts predicted that the jet's successful breakout would be followed by a more traditional, though still immensely powerful, supernova explosion. Days after the gamma rays faded, astronomers trained their optical telescopes on the location and witnessed exactly that. The event now designated SN 2013 CW appeared, a supernova whose characteristics perfectly matched the explosion of a massive hydrogen-stripped star. This was the final, conclusive piece of the puzzle. The same core collapse that created the black hole and powered the jets also sent a spherical shockwave outward through the rest of the star. This shockwave, arriving later and moving much slower than the relativistic jets, blew the entire star apart in a supernova that was, by itself, hundreds of times more energetic than a typical stellar explosion. This combination is the very definition of a hypernova, a supernova powered by a central engine of a black hole and an accretion disk. GRB 130427 was therefore a Rosetta Stone event. It beautifully and unambiguously connected three distinct phenomena: the long gamma-ray burst, the hypernova, and the birth of a new black hole. It demonstrated that these are not separate events, but different facets of the same catastrophic process, viewed from different angles and at different times. The energy budget involved is staggering. In just those few seconds of the gamma-ray burst, the jets released more energy than our Sun will emit over its entire 10 billion-year lifetime. The subsequent hypernova then released a comparable amount of energy, but in a more spherical, slower-moving explosion. This two-stage process, a directed beam of pure fury followed by an omnidirectional blast, represents one of the most efficient and destructive ways for a star to end its life. It is a stark reminder that the alignment of a star's spin and our line of sight can transform a distant stellar collapse into a cosmic beacon, visible across billions of light years and illuminating the most violent physics in the universe. As we've seen, black holes are not just passive gravitational sinks. They are dynamic engines of destruction that can unleash incredible power when provided with fuel. But what happens when that fuel is not a steady stream of gas, but an entire, intact star? The answer is one of the most violently beautiful events in the cosmos, earning the number 10 spot on our countdown. The tidal disruption event, perfectly exemplified by the cataclysm known as Assassin 14 Lie. Discovered in November 2014 by the All-Sky Automated Survey for Supernova, this event occurred in the center of a galaxy about 290 million light-years away. It wasn't the death of an unstable star from within, but a murder from without, a stellar execution carried out by the gravitational tides of a supermassive black hole. The process begins with a star, much like our own Sun, following an orbit that carries it perilously close to the dormant monster at the galactic center. Every object in space experiences tides. Our own oceans rise and fall due to the Moon's gravitational pull being stronger on the side of Earth facing it. Now amplify that effect by a factor of 1 billion. As the star approaches the black hole, the side closest to the gravitational behemoth feels a force immeasurably stronger than the side farthest away. This difference in gravity, the tidal force, relentlessly stretches the star. It is no longer strong enough to hold itself together against this cosmic tug of war. The star is progressively pulled into a long, thin strand of incandescent gas, a process physicists poetically call spaghettification. It's a fundamental transformation from a spherical, nuclear-fusing ball of plasma into a shimmering river of stellar debris. This is only the beginning of the destruction. The black hole's gravity doesn't just stretch the star, it ultimately overcomes the nuclear bonds that hold it intact, completely shredding it. About half of the stellar debris is flung outwards at incredible speeds, cast into the darkness of interstellar space, never to return. The other half, however, is captured by the black hole's gravity. This material doesn't fall straight in. Instead, it forms a vast, swirling accretion disk around the event horizon, a frantic whirlpool of superheated gas and plasma. As this material spirals inward, rubbing against itself under immense pressure, it heats to temperatures of millions of degrees. This frantic motion converts an enormous amount of gravitational potential energy into heat and light, causing the black hole's immediate environment to flare with a brilliance that can briefly outshine every star in its host galaxy combined. This is the flash that surveys like assassin detected the death scream of a star, converted into a beacon of electromagnetic radiation. What made Assassin 14 lie a landmark event was not just its discovery, but the incredible detail in which it was observed across the entire electromagnetic spectrum. This was not a fleeting, one-wavelength flash. Astronomers detected its powerful signature in visible light, ultraviolet radiation, and perhaps most importantly, in X-rays. The intense X-ray emission served as a direct probe into the hottest, innermost regions of the newly formed accretion disk, just outside the point of no return. For the first time, scientists could watch the structure of this disk evolve in real time, seeing how the rate of material falling into the black hole changed over weeks and months. It was like watching a cosmic waterfall in slow motion, providing an unprecedented view of how a black hole feeds. This detailed observation transforms tidal disruption events from mere cosmic spectacles into precision tools for astronomy. Most supermassive black holes in the universe, including the one at the heart of our own Milky Way, are dormant and incredibly difficult to study directly. They are, by their very nature, dark, but when a star is torn apart, it effectively turns on a bright light in the darkness, illuminating the black hole's properties. By analyzing the light curve of the flare, how quickly it brightens and how slowly it fades, astronomers can estimate the mass of the central black hole. The duration and intensity of the event are directly tied to the gravitational grip of the unseen monster. Furthermore, the composition of the stellar debris, revealed through spectroscopy, tells us about the type of star that was destroyed. Assassin 14 Live, for instance, provided evidence that the victim was a Sun-like star, giving us a complete picture of the victim and the perpetrator in a single, catastrophic event. The legacy of events like Assassin 14 Live is a profound shift in our understanding of galactic centers. They reveal that the quiet, dark voids we often picture are actually sites of recurring, violent drama. A supermassive black hole is not a static trapdoor, it is an active predator, and the occasional passing star is its meal. Each tidal disruption event is a brilliant, temporary resurrection of a quasar, offering a fleeting opportunity to measure the immeasurable and to study the feeding habits of the cosmos's most enigmatic objects. They are stark reminders that even in the vast emptiness of space, a wrong turn can lead to a spectacular and terrifying end, all while providing the light we need to understand the darkness. At number 11, we voyage back to the very dawn of cosmic time, to an explosion that serves as a direct messenger from the universe's infancy. This is GRB 090423, a gamma-ray burst detected in April 2009. In a fleeting flash of high-energy radiation that lasted barely 10 seconds, this object claimed a profound title, the most distant and therefore the oldest object ever identified by humanity at that time. The numbers involved are truly humbling. The light from this burst traveled for approximately 13 billion years before finally washing over our telescopes. We are witnessing an event that occurred when the cosmos itself was a mere 600 million years old, a toddler by universal standards. To put that into perspective, our own solar system would not even begin to form for another 8 billion years. This was not just an explosion, it was a beacon from the cosmic dark ages, a signal from an era when the universe was undergoing its most fundamental transformation. The sheer existence of such a powerful explosion so early in the universe's history is in itself a monumental discovery. Gamma-ray bursts of this nature, as we have learned, are the death cries of massive, rapidly spinning stars collapsing into black holes. The presence of GRB 090423 so soon after the Big Bang tells us one crucial thing. The first generations of stars had already been born, lived their furious lives, and died by this point. And they must have been incredible stars. Theoreticians call them population 3 stars, the very first stars to ignite in the primordial cosmos. Formed from the pristine hydrogen and helium forged in the Big Bang, with no heavier elements to cool their cores, these stars are thought to have been cosmic leviathans, many containing the mass of hundreds of our suns. Such monstrous stars would have burned at ferocious temperatures and exhausted their nuclear fuel in just a few million years, a cosmic blink of an eye. Their deaths in violent collapses and subsequent gamma-ray bursts would have been commonplace events in that young, turbulent universe. GRB 090423 is our strongest direct evidence that these mythical first stars were not only real, but that they could indeed end their lives in the most spectacular fashion imaginable. Beyond confirming the life cycle of the first stars, this ancient fireball provides a critical clue to one of the most important periods in cosmic history, the epoch of reionization. For the first several hundred million years after the Big Bang, the universe was a dark, foggy place. It was filled with a dense, neutral hydrogen gas that absorbed the energetic ultraviolet light from the earliest stars and galaxies, preventing it from traveling far. The universe was trapped in a cosmic dark age, but something happened to clear this fog. That something was an immense flood of ultraviolet radiation and X-rays, powerful enough to strip electrons from the hydrogen atoms, reionizing the gas and transforming the universe from opaque to transparent. For decades, astronomers have debated the primary sources of this ionizing radiation. Were it small, numerous early galaxies, or were the first, incredibly massive stars the main drivers? The detection of GRB 090423 strongly suggests that the deaths of these first stars played a pivotal role. A long gamma-ray burst is more than just a momentary flash. It is the signature of a hypernova, an explosion that floods its surroundings with an immense amount of high-energy ultraviolet and X-ray radiation. In the cramped, gas-rich neighborhoods of the early universe, the blast from a single event like this could have blown a vast, transparent bubble in the neutral hydrogen, like a powerful lighthouse beam punching through a dense sea fog. Multiply this effect by the thousands of similar explosions that must have occurred across the young cosmos, and you have a compelling mechanism for helping to clear the universal haze. This single burst of light, observed for 10 seconds in 2009, tells us that the violent deaths of the very first stars were not just endings. They were active participants in sculpting the transparent cosmic landscape that would eventually allow galaxies like our own to form and evolve. The technological feat of detecting such a faint, ancient signal cannot be overstated. The swift satellite, which first detected the gamma-ray flash, immediately alerted ground-based observatories. Astronomers raced against the setting sun and the rotation of the Earth, training the world's most powerful infrared telescopes on the rapidly fading afterglow. They were successful because they were looking in infrared light. The expansion of the universe has stretched the original visible and ultraviolet light from the burst so dramatically over its 13 billion-year journey that it arrived at Earth as faint infrared radiation. Catching this afterglow was like capturing the last whisper of a shout from the edge of time itself. GRB 090423 now stands as a milestone in observational cosmology. It pushed our observational frontiers to a new limit, proving that we can indeed peer back into the first few percent of the universe's existence and directly study the forces that shaped everything that was to come. It is a timeless reminder that even the most transient events can illuminate the deepest secrets of our origins. Now we pivot from the cataclysmic deaths of the first stars to a stellar explosion that is uniquely our own, an event witnessed by human eyes and recorded in ancient annals, forever linking our story to the cosmos. At number 12, we encounter a supernova that not only illuminated the sky but fundamentally bridged the gap between historical observation and modern science. The supernova of 1054, the progenitor of the magnificent Crab Nebula. In the early morning of July 4, 1054, astronomers in Song Dynasty China and across the Islamic world looked up to see a new, brilliant star appear in the constellation of Taurus. To them, it was a guest star, a temporary visitor that shone with an intensity rivaling the planet Venus. So bright it was visible in broad daylight for 23 consecutive days and remained naked eye visible in the night sky for nearly 2 full years. These meticulous court records, along with those from Japanese and Arab scholars, provide an invaluable astronomical gift, a precise timestamp for one of the universe's most dramatic events, allowing modern scientists to know exactly when the light from this cosmic cataclysm first reached Earth. For centuries, this guest star was a historical curiosity, a bright point in old texts. Then, in the 1700s, astronomers using early telescopes discovered a faint, fuzzy patch of light in the exact same location. This nebula was catalogued and observed, but its true nature remained a mystery until the 20th century. We now understand that this wispy cloud, the Crab Nebula, is the expanding debris field from that very 1054 explosion, a cosmic crime scene where we have both the eyewitness accounts and the physical evidence. Located about 6,500 light-years away, the nebula is a dynamic, ever-changing structure, its filaments of gas expanding outward at over 1,000 kilometers per second. Modern observations across different wavelengths reveal its incredible complexity, a tapestry of glowing hydrogen and oxygen, threaded with filaments of dust, all shining because they are energized by a powerhouse at the very center of the blast zone. That central powerhouse is the true legacy of the supernova, the stellar corpse left behind after the star's core collapsed. In the 1054 event, the star was not massive enough to create a black hole. Instead, its core was crushed into an ultra-dense sphere of neutrons, a city-sized object containing more mass than our entire sun. This is the Crab pulsar, and it is one of the most studied objects in the sky. A pulsar is a rapidly spinning neutron star that emits beams of radiation from its magnetic poles. Like a cosmic lighthouse as the star rotates in the Crab's case, an astounding 30 times every second, these beams sweep across space. If one of those beams happens to cross our line of sight, we detect a regular pulse of radiation. The energy released by this frantic spin down is truly colossal. The pulsar loses an immense amount of rotational energy, which is channeled into the surrounding nebula, causing the entire cloud to glow relentlessly across the electromagnetic spectrum, from radio waves all the way up to gamma rays. This singular event, SN 1054, stands as a foundational pillar of modern astrophysics. It provided the first clear, undeniable link between a historical supernova observation and a visible nebula remnant, confirming that these nebulae were indeed the expanding clouds from stellar explosions. The Crab Nebula and its pulsar became the perfect natural laboratory. By studying how its pulsar gradually slows down, physicists can test theories of gravity and the behavior of matter at nuclear densities. The nebula itself acts as a giant particle accelerator, its tangled magnetic fields accelerating electrons to near light speed, producing the brilliant synchrotron radiation that makes it such a prominent object. It is a constant, dynamic reminder that the universe is not a static picture, but a living, evolving system. The flash of light seen by an imperial astronomer nearly a millennium ago continues to illuminate our understanding of stellar life cycles, the birth of exotic objects, and the raw physics that governs the universe's most powerful transformations. And now we arrive at an explosion that was not merely observed by distant telescopes, but one that was felt, a stellar death that delivered a tangible piece of its heart directly to our planet. At number 13, we have Supernova 1987A, a celestial event of unprecedented proximity and scientific fortune. On February 23, 1987, a star named Sanjulik -69°202, located in the Large Magellanic Cloud, a small satellite galaxy of our Milky Way, reached the end of its life. For the first time in over 3 centuries, a supernova was visible to the naked eye from Earth, a new star igniting in the southern sky. Though it was 168,000 light-years away, this was, in cosmic terms, right in our own backyard. What followed was not just a visual spectacle, but a revolution in our understanding of how massive stars die. An event that confirmed a central pillar of astrophysical theory with a torrent of ghostly particles. The very first signal from the exploding star did not arrive as light. Hours before the flash became visible on Earth, a surge of nearly 24 tiny, nearly massless particles called neutrinos passed through 3 enormous underground detectors, one in Japan, another in the United States, and a third in Russia. This was a landmark moment, the birth of extrasolar neutrino astronomy. These neutrinos were the direct, immediate byproduct of the star's core collapsing, a process that crushes an iron core the size of Earth into an ultra-dense neutron star just a few miles across in a fraction of a second. In that unimaginable compression, 99% of the gravitational energy is carried away by a flood of neutrinos. For about 10 seconds, these messengers screamed out from the heart of the collapse, confirming a decades-old prediction that the core collapse of a massive star is what powers a supernova. They were the death notice from the stellar core, delivered hours before the shockwave finished ripping its way through the star's outer layers to create the brilliant flash we would eventually see. As the light from 1987 brightened, astronomers began to piece together the fascinating life of the star that had just perished. Unlike the red supergiants typically expected for such explosions, the progenitor was a blue supergiant. This revelation forced a major re-evaluation of stellar evolution models, suggesting that the star had shed a significant amount of its outer envelope before exploding, transforming from a red to a blue supergiant in its final stages. The visual spectacle of the supernova itself was stunning, but the real, long-term legacy has been the decades-long watch of its evolving remnant. The expanding cloud of debris presented astronomers with a gift, a complex, 3-ringed structure that had been ejected by the star tens of thousands of years before its final demise. This iconic triple-ring structure, revealed in exquisite detail by the Hubble Space Telescope, resembles a cosmic hourglass with a central, expanding debris cloud flanked by two large outer rings and a faint inner ring. The origin of this beautiful structure is tied to the star's turbulent final millennia. The prevailing theory suggests that in its death throes, the star experienced a violent, convulsive merger with a smaller companion star, flinging rings of gas into space in a complex bipolar outflow. Alternatively, the rings could be the result of a furious stellar wind from the rapidly spinning, dying star, shaped by an intense magnetic field. Regardless of their precise origin, these rings have provided a fixed reference frame against which we can watch the supernova's blast wave expand in real time. For years, astronomers watched and waited as the central debris cloud, expanding at thousands of kilometers per second, slowly closed the gap to the inner ring. Then the collision began. In the late 1990s, the outward-moving shock wave finally slammed into the inner ring of dense, relatively stagnant gas. The effect was like throwing a switch on a cosmic power grid. The collision heated the ring material to millions of degrees, causing it to ignite in a brilliant display of X-rays and visible light. Dozens of bright, hot spots appeared like pearls on a necklace as the shock wave lit up different sections of the ring. This ongoing interaction has turned the remnant into a dynamic, real-time physics laboratory. We are witnessing the process of stellar enrichment happening right before our eyes, as the heavy elements forged in the star's core, and during the explosion itself, elements like oxygen, carbon, and silicon are violently injected into the surrounding ring, seeding the interstellar medium with the building blocks for future stars and planets. Decades after its light first reached us, supernova 1987 remains one of the most intensely studied objects in the sky. The central, lingering mystery is the final fate of the core. While the neutrino data confirmed the formation of a neutron star, no pulsar has yet been detected. It is possible that the newborn neutron star is enshrouded by a thick veil of dust, its beacon temporarily hidden. Or perhaps it collapsed further into a black hole, though the timing of the neutrino burst makes that less likely. Every new observation with cutting-edge telescopes brings us closer to an answer. This single event, a fleeting naked eye star from 37 years ago, has provided a complete multi-messenger case study of stellar death. It connected theory with direct observation, confirmed the role of neutrinos, and gave us a front-row seat to the long-term aftermath of an explosion. It is a unique and precious laboratory, a continuing gift from a neighboring galaxy that keeps on revealing the intricate, violent, and beautiful processes that govern the end of a star's life. Returning to the monumental event GW170817, we can now focus on a specific, razor-sharp component of that cataclysm, the short gamma-ray burst that announced it to the cosmos. This 2-second flash of high-energy radiation, detected just moments after the gravitational wave signal, was far more than a coincidence. It was the definitive signature of the merger's final, violent act. Unlike the long-duration gamma-ray bursts we explored earlier, which are theatrical productions lasting from 2 seconds to several minutes and are powered by the collapse of massive stars, short GRBs are the universe's staccato notes. They are incredibly brief, typically lasting less than 2 seconds, and their origin was one of the most sought-after prizes in high-energy astrophysics. For decades, the leading theory pointed toward the merger of two ultra-dense objects, either two neutron stars or a neutron star and a black hole. The idea was that in the final frantic moments before coalescence, the incredible tidal forces and magnetic fields involved could launch ultra-fast jets of matter, and if one of those jets was pointed at Earth, we would see it as a short, brilliant burst of gamma rays. GW170817 was the first time we ever caught one of these mergers in the act, providing the direct, smoking gun evidence that confirmed this long-held hypothesis. The mechanics of this specific short GRB were a masterpiece of extreme physics. As the two neutron stars spiraled inward, their final orbits took only milliseconds to complete. In the last instant before they merged into a single object, likely a black hole, a tiny fraction of their combined mass was ejected and swirled around the newborn remnant at velocities approaching the speed of light. This created a phenomenally hot and dense accretion disk, a whirlpool of pure neutrons and energy. From the poles of this maelstrom, powered by the remnant's intense rotation and magnetic fields, a pair of narrow jets erupted. These jets had to fight their way out, but unlike in a long GRB where they must punch through the massive envelope of a giant star, here the path was relatively clear. The jet that generated GRB 170817 was able to escape almost unimpeded, and its 2-second duration perfectly matched the theoretical models for the timescale of a jet being launched from a neutron star merger. We were not just seeing a flash, we were seeing the birth of a relativistic jet from one of the most energetic events imaginable. What made this observation so revolutionary was the multi-messenger nature of the discovery. The gravitational waves told us what was happening, the in-spiral and merger of two neutron stars. The short gamma ray burst then told us how that merger manifested itself in one of the most energetic electromagnetic phenomena known. This 1-2 punch of information eliminated any remaining doubt about the origin of at least a significant population of short GRBs. It connected a specific, fleeting flash in the gamma ray sky directly to a specific type of cataclysmic event measured through ripples in spacetime. This was the equivalent of a detective not only hearing the gunshot but also seeing the bullet leave the barrel and tracing its path back to the shooter, all with different complementary senses. The faintness of the gamma ray burst itself was also a critical piece of the puzzle. It was about 1,000 times less energetic than a typical short GRB detected from much farther away, which perfectly fit the narrative that we were seeing the event from a slight off-axis angle. We weren't looking directly down the barrel of the jet, but were catching it from a slightly oblique viewpoint, which made the flash appear weaker but allowed us to see the subsequent kilonova in all its glory. This single event tied together the gravitational wave universe, the high-energy gamma-ray universe, and the optical universe into one coherent, breathtaking story of creation and destruction. Leaving behind the single, catastrophic blasts of supernova and mergers, we now encounter an explosion playing out in slow motion, a continuous, high-velocity eruption that has been carving its way through the galaxy for millennia. At number 15, we find the runaway pulsar PSRB 2224+65 and its extraordinary wake, the Guitar Nebula. This is not a one-time detonation you can point to in the sky. It is a relentless, ongoing release of power, a stellar engine that has torn itself from the site of its birth and is now rocketing through the void, leaving a brilliant scar in its wake. The pulsar itself is moving at an almost incomprehensible speed, clocked at over 1,500 kilometers per second, or about 3.5 million miles per hour. At that velocity, it could travel the distance from Earth to the Moon in a mere 4 minutes. But its sheer speed is only half the story. The true spectacle is the interaction between this cosmic cannonball and the delicate, wispy gas of the interstellar medium. Imagine a speedboat racing across a still lake, its bow pushing the water aside in a V-shaped wave. The Guitar Nebula is the cosmic equivalent of that wave, but written in glowing gas and energized by one of the most powerful objects in the universe. As the pulsar hurtles through space, it doesn't travel in perfect silence. It is a rapidly spinning neutron star, a remnant of a past supernova, and it possesses a ferocious magnetic field and a powerful wind, a stream of charged particles flung outward from its surface at near light speed. This is the pulsar wind, a continuous, relativistic blast of electrons and positrons. When this supersonic wind slams into the nearly stationary, tenuous hydrogen gas that fills the space between stars, it creates a phenomenon known as a bow shock. The collision is so violent that it compresses and heats the interstellar gas, making it glow with a faint, ethereal light. This glowing wall of gas is what forms the distinctive body of the guitar, while the pulsar itself, located at the tip of the neck, is the invisible hand that strums the strings. The unique guitar-like shape of the nebula is a direct result of the pulsar's motion. The head or the body of the guitar is the bright, compressed bow shock directly in front of the pulsar as it plows through space. The long, thin neck trailing behind is the pulsar's wake, a tunnel of less dense gas that has been swept clear and excited by the pulsar's powerful wind. This entire structure is a dynamic laboratory, allowing us to study the interaction between a relativistic particle beam and the interstellar medium in real time. The energy required to inflate and illuminate such a structure is staggering, and it all comes from the spin of the pulsar itself. Every bit of light we see from the guitar nebula is energy being siphoned directly from the pulsar's rotation, a gradual breaking process that will, over millions of years, cause it to spin down and its wind to weaken. This raises a fascinating question. How did this pulsar acquire such an incredible velocity in the first place? It did not get this speed from the supernova that created it alone. While a supernova explosion can be slightly asymmetrical, giving the newborn neutron star a kick, the velocities observed here are far too high for that to be the sole explanation. The most likely scenario is that the pulsar was once part of a binary star system. When its more massive companion star reached the end of its life and exploded as a supernova, the system was violently disrupted. The explosion would have been suddenly lopsided, ejecting the companion star and flinging the pulsar away like a stone from a slingshot. Alternatively, if the companion star exploded and collapsed into a black hole or another neutron star, the subsequent gravitational interactions could have catapulted the pulsar out of the system at these extreme speeds. PSRB 2224 plus 65 is a runaway, a celestial orphan cast out from its stellar family and destined to travel the galaxy alone, its powerful wind etching its path across the cosmos for all to see. It is a different kind of explosion, not a sudden flash, but a persistent sculpting force, a testament to the enduring power locked within the spinning heart of a dead star. As we have seen, stars often send out clear signals before their final demise, but what happens when a star begins to cry wolf, staging dramatic outbursts that blur the line between a tantrum and a terminal event? This brings us to number 16, the perplexing case of SN 2009 IP, a celestial drama that unfolded over several years and challenged astronomers to define the exact moment of stellar death. Located in the galaxy NGC 7259, about 70 million light-years away, this object was not a calm, stable star. It was identified as a luminous blue variable, a class of massive, hypergiant stars that are notoriously unstable, prone to violent episodes where they shudder and expel huge amounts of their own mass into space. For years, SN 2009 IP was just that, a variable star brightening and dimming in a predictable pattern of instability. But then, in 2009, it did something new and dramatic, brightening significantly in an event that was initially classified as a supernova. That's where it got its SN designation, even though the star, astonishingly, survived this first major eruption. What followed was a period of sustained stellar theatrics. Over the next 3 years, the star continued to experience powerful outbursts, ejecting shells of gas that expanded outward and created a complex, layered circumstellar environment. Imagine a star constantly shedding its skin, surrounding itself with cocoons of its own previously ejected material. Each new eruption plowed into the debris from the last, creating shocks and emitting brilliant light. Astronomers watched, fascinated, as this star seemed to be teetering on the brink, putting on a spectacular show of stellar agitation. They knew luminous blue variables like Eta Carinae were capable of these supernova impostor events, but SN 2009 IP was pushing the boundaries of what was considered mere impostor behavior. The energy release in these pre-supernova outbursts was immense, each one comparable to a significant fraction of a true supernova's power. The stage was being set layer by layer for a final, decisive act. Then, in the summer of 2012, the star appeared to deliver its final performance. It flared up with a brilliance that dwarfed all its previous outbursts, becoming millions of times brighter than our Sun. Observations showed light curves and spectral signatures that were, for all intents and purposes, identical to those of a genuine core collapse supernova. The expanding shockwave was measured moving at incredibly high velocities, over 10,000 kilometers per second, a clear hallmark of a stellar core collapsing and a shockwave blasting outward. The consensus at the time was that the wolf had finally arrived, the star's core had imploded, and this was the real, final supernova. The long-running drama of SN 2009 IP seemed to have reached its inevitable explosive conclusion. Yet the story refused to end so neatly. In the months and years that followed, a fierce debate ignited within the astronomical community. Some researchers argued that the 2012 event was indeed the terminal explosion, pointing to the high velocities and the classic supernova light curve as unequivocal proof. According to this view, the star had finally exhausted its nuclear fuel, its core had collapsed, and it was now an expanding cloud of debris, potentially with a neutron star or black hole at its center. The prior outbursts were simply the final, desperate struggles of a dying star, violently shedding its outer layers in the centuries and years leading up to the ultimate collapse. The fate of the star was sealed. However, a compelling counter-argument emerged, suggesting something even more extraordinary, that the star might have somehow survived. Proponents of this theory pointed to the star's subsequent behavior. After the 2012 event, the light from the object did not fade away completely as expected for a supernova. Instead, it plateaued and then showed signs of re-brightening, as if a central engine was still active and powering the emission. The leading hypothesis for this survival scenario is that the 2012 event was not a core collapse supernova, but an exceptionally powerful pulsational pair instability eruption. In this model, the star's core becomes so hot that radiation pressure triggers runaway pair production, leading to a partial explosion that blows off the star's outer layers in a cataclysmic eruption, but leaves the core intact to continue nuclear fusion. The star essentially experiences a supernova strength blast without actually dying, a seismic event that ejects a colossal amount of mass but allows the stellar heart to keep beating, potentially setting the stage for an even larger final explosion in the future. This ongoing debate over SN 2009 IP is far more than academic. It strikes at the very heart of how we classify stellar death and understand the final moments of the most massive stars. It forces astronomers to ask a fundamental question: what is the definitive signature of a star's end? Is it the instantaneous collapse of the core, or is it the complete and total disintegration of the star? SN 2009 IP demonstrates that the boundary between a giant outburst and a genuine supernova can be astonishingly blurry. It reveals that the death process for these stellar behemoths may not be a single moment, but a drawn-out series of escalating convulsions, a prolonged farewell that can last for decades. This object serves as a critical case study, teaching us that the universe often resists our neat categorizations and that the most powerful explosions can sometimes be survivable. But sometimes the most breathtaking view of an explosion is not the initial flash, but the lingering ghost it leaves behind, an ethereal afterimage that tells a story of ancient violence. Claiming the number 17 spot is the magnificent Vela supernova remnant, the fading echo of a star that died roughly 11,000 years ago, long before the dawn of recorded human history. Located a mere 800 light-years away, this is one of the closest supernova remnants to Earth, a vast and intricate nebula that sprawls across an area of the sky equivalent to over 20 full moons. If our eyes were sensitive enough to see its full glory, it would be one of the largest and most spectacular sights in the heavens. Instead, we rely on telescopes to reveal its true splendor, and in multiple wavelengths of light, the Vela remnant transforms into a celestial tapestry of breathtaking complexity. In visible light, it appears as a delicate web of glowing pink and orange filaments, like a cosmic lacework spun from the incandescent guts of the exploded star. These filaments are shock waves, the actual leading edge of the blast still plowing through the interstellar medium at supersonic speeds, heating the gas and causing it to glow. The true scale of this ancient cataclysm, however, is best appreciated in other parts of the electromagnetic spectrum. X-ray observations reveal a different, more energetic component of the remnant, a gigantic spherical bubble of gas heated to millions of degrees, a testament to the raw thermal energy released in the initial detonation. This hot, thin plasma fills the interior of the expanding shell, a ghostly sphere of immense heat. Meanwhile, radio telescopes map out the faintest outer edges of the blast wave as it continues its slow-motion expansion into the cold void of space. This multi-wavelength view gives us a complete three-dimensional understanding of the remnant structure. We can see the dense, knotty filaments of the shock front, the hot, diffuse interior, and the delicate tracery of magnetic fields that thread through the entire structure, all working together to paint a portrait of an explosion frozen in time, yet still dynamically evolving. This is not a static monument, it is an active crime scene where the physics of stellar death is still playing out, 11 millennia after the fact. At the very heart of this beautiful chaos lies the engine, the reason this ghostly cloud continues to shine so brightly, the Vela pulsar. This tiny, city-sized object is the collapsed core of the original massive star, a neutron star spinning with incredible velocity. It completes over 11 full rotations every single second, and with each spin, it acts like a powerful cosmic lighthouse. Beams of radiation from its magnetic poles sweep across space, and one of those beams regularly crosses our line of sight, resulting in a rhythmic pulse of radio waves, visible light, and even gamma rays that we can detect with our instruments. The Vela pulsar is not just a silent relic, it is a hyperactive dynamo, and its relentless spin is the power source for the entire nebula. The pulsar generates an intense supersonic wind made of electrons and positrons, a relentless stream of charged particles that screams outward from the neutron star. This pulsar wind slams into the slower-moving debris of the supernova remnant that surrounds it, re-energizing the gas and creating a brilliant, intricate nebula within the larger nebula. This structure, known as a pulsar wind nebula, is like a constantly stoked fire at the center of the expanding ashes. The wind injects fresh energy into the system, exciting the gas and causing it to glow across various wavelengths, long after the initial heat from the supernova blast would have faded away. It is this central engine that keeps the Vela supernova remnant looking so vibrant and youthful. Without the pulsar's constant energy input, this magnificent structure would have faded into near invisibility millennia ago, a faint and dissipating cloud. The Vela pulsar is the beating heart of the remnant, a reminder that the death of a star often gives birth to something equally powerful and dynamic. The proximity of the Vela remnant offers us a profound and slightly unsettling connection to this ancient event. A supernova occurring a mere 800 light-years away would have been a spectacular sight for any early humans who witnessed it. While there are no historical records, it is conceivable that our ancestors saw a brilliant new star appear in the sky, potentially rivaling the moon in brightness for a period of weeks or months. More significantly, such a nearby explosion would have bathed the Earth in a shower of radiation and cosmic rays. While it was likely too distant to cause a mass extinction, it may have subtly influenced our planet's atmosphere and the radiation exposure of life on the surface. Studying the Vela remnant, therefore, is not just an exercise in astronomy. It is a way of investigating our own local cosmic environment and understanding the forces that have shaped our galactic neighborhood. It stands as a majestic and beautiful monument to a stellar catastrophe, a continuous explosion powered by a spinning corpse, teaching us that in the cosmos, even death can be a source of enduring light and incredible structure. While we have been gazing across the cosmos at the deaths of stars and the mergers of black holes, it is a sobering fact that one of the most potent explosions to directly affect our world originates from the very star that gives us life. At number 18, we turn our attention from the distant and exotic to the intimately familiar, yet no less powerful, a solar superflare. Our sun may seem a model of consistency, a placid yellow ball in the sky, but it is a seething, dynamic ball of plasma, and its relatively calm demeanor is a temporary phase in a long and volatile life. The historical record, and even the geological one, provides chilling evidence that our sun is capable of eruptions of such ferocity that they can literally leave their mark on our planet. In the year 775, an event of unimaginable power occurred on the solar surface, an explosion so intense that its signature was locked away not in human chronicles, but in the very growth rings of ancient trees and the pristine layers of polar ice. Scientific detectives analyzing carbon-14 levels in tree rings from that period discovered a colossal and sudden spike. This isotope, carbon-14, is normally created when cosmic rays from deep space strike our atmosphere. For there to be such a pronounced and isolated increase, the Earth must have been bombarded by an immense wave of radiation, a flood of high-energy protons that could only have come from our own sun. The event was a perfect storm of solar violence, a solar superflare likely accompanied by a colossal coronal mass ejection. This is not a simple solar flare, which is a flash of intense radiation. A superflare is a magnetically driven explosion on an epic scale, where the sun's tangled magnetic field lines reconfigure in a cataclysm of energy release, hurling billions of tons of superheated plasma and a blizzard of atomic particles directly into space at millions of kilometers per hour. The event in 775 was so powerful that it dwarfed any solar activity observed in the modern era, including the famous Carrington event of 1859, which set telegraph offices on fire and produced auroras as far south as the Caribbean. The mechanism behind such an explosion is a testament to the raw power contained within the sun's magnetic furnace. The solar surface is a chaotic tapestry of magnetic loops and sunspots, regions where the star's inner magnetic field bursts through the photosphere. When these field lines become overly twisted and stressed, they can snap and reconnect in a process of immense violence. This magnetic reconnection acts like a cosmic slingshot, instantaneously converting monumental magnetic energy into thermal energy, particle acceleration, and light. It is this process that can launch a coronal mass ejection, a billion-ton cloud of magnetized plasma, on a collision course with Earth. In 775, one of these titanic projectiles aimed directly at our planet slammed into our magnetic field. The resulting geomagnetic storm and radiation shower was so intense it altered the very chemistry of our upper atmosphere, creating an excess of carbon-14 that was then absorbed by growing plants, creating a permanent radioactive barcode of the event in the world's oldest trees. Had an event of this magnitude occurred in our hyper-connected, technology-dependent 21st century, the consequences would be nothing short of catastrophic on a global scale. The initial blast of X-rays and extreme ultraviolet radiation would arrive at the speed of light, violently ionizing the upper atmosphere and causing widespread radio blackouts, crippling all forms of satellite communication and GPS navigation instantly. Then, within a day or so, the coronal mass ejection itself would arrive. When this magnetized cloud of solar plasma engulfed Earth, it would compress our planet's protective magnetic field to dangerously low levels and induce powerful electrical currents in the ground. These geomagnetically induced currents would surge through our longest conductors, our power grids, high-voltage transformers. The massive, difficult-to-replace hearts of our electrical infrastructure would be overloaded and fried, plunging entire continents into darkness. The cascading failure could take months or even years to repair, leading to a collapse of modern civilization as we know it, with no electricity for water treatment, refrigeration, healthcare, or financial systems. The aftermath would extend far beyond our planet's surface. The intense radiation storm would pose a severe danger to astronauts aboard the International Space Station, who would need to take shelter in the most heavily shielded sections of their craft. The thousands of satellites orbiting Earth, which form the backbone of global communications, weather forecasting, and military operations, would be bombarded. Their delicate electronics would be fried by the particle onslaught, creating a halo of permanent space junk that would render low Earth orbit unusable for generations. This is not science fiction. It is a stark and plausible scenario based on an event that has already happened. The 775 superflare serves as a humbling reminder that the most powerful explosions are not always those that occur in far-off galaxies. Sometimes the most transformative and dangerous cosmic events are those that erupt from our own local star, a constant, life-giving companion that also holds the power to reset the clock on human technological achievement with a single, magnetically driven tantrum. But what if the most immense explosion in the cosmos isn't a brilliant flash of light or a gravitational wave, but a silent, universe-wide process that has been unfolding since the dawn of time? This brings us to a different kind of detonation altogether, one that doesn't tear through space, but rather is space, or at least the invisible scaffold that holds it all together. At number 19, we venture into one of the most profound and speculative frontiers of modern physics with a potential explosion of a fundamental particle, the mystery of the 3.5 kiloelectronvolt line. This isn't an event you can point a telescope at and see. It's a ghost in the machine, a faint, persistent whisper in the X-ray spectrum that could be the first indirect evidence of dark matter annihilating or decaying right before our eyes, a slow-motion explosion on a cosmological scale. The story begins not with a dramatic burst, but with a meticulous, line-by-line analysis of data. For decades, astronomers have known that the universe is filled with far more mass than we can see. The way galaxies spin and the way galaxy clusters move all point to the existence of a mysterious, invisible substance that provides the extra gravity to hold everything together: dark matter. We know it's there by its gravitational effects, but we have never directly detected what it's made of. Then, starting around 2014, multiple independent teams, using different X-ray space telescopes like NASA Chandra and the European Space Agency's Newton, began to notice something peculiar. When they looked at the combined X-ray light from massive galaxy clusters like Perseus, or even from our neighboring Andromeda galaxy, they consistently found a faint, unexpected spike in the data at a very specific energy, 3.5 kiloelectronvolts, or 3.5 keV for short. This was an emission line that didn't correspond to any known atom or molecule. It was an anonymous signal, a signature with no known author, appearing in the darkest, most massive structures in the universe. The immediate and most thrilling hypothesis was that this faint X-ray line could be the long-sought-after fingerprint of dark matter itself. The leading candidate to explain it is a hypothetical particle known as a sterile neutrino. Unlike the active neutrinos that flood the universe and interact via the weak nuclear force, sterile neutrinos would, as their name implies, be aloof. They would interact with ordinary matter only through gravity, making them perfectly invisible and an ideal candidate for dark matter. The theory suggests that these sterile neutrinos are not completely stable. Occasionally, and on cosmic timescales, a sterile neutrino could spontaneously decay into an ordinary, active neutrino and a photon, a particle of light. The energy of that photon, dictated by the mass of the original sterile neutrino, would be precisely 3.5 keV. What astronomers were potentially seeing was not a localized blast, but the collective, universe-wide glow from the slow, steady decay of these invisible particles. Every faint X-ray photon at that specific energy would be the death rattle of a piece of the cosmic dark matter skeleton, a tiny, fundamental explosion happening everywhere at once. To grasp the scale of this proposed phenomenon, you have to shift your perspective entirely. This isn't an explosion confined to a single star or galaxy. If the 3.5 keV line is indeed from dark matter decay, then it represents a continuous, ubiquitous process. Every cubic light-year of space that contains dark matter is, in a sense, glowing with this faint X-ray light. It is a slow-motion detonation that has been ongoing for billions of years, a background hum of creation and destruction woven into the fabric of the cosmos itself. The reason we see it most strongly in galaxy clusters and the Andromeda galaxy is simply because that's where dark matter is most densely concentrated. We're looking at the brightest patches of this universal, ethereal glow. The energy release for any single decay is minuscule, but when you multiply it by the countless trillions upon trillions of sterile neutrinos that may make up the dark matter halo of a galaxy cluster, it adds up to a detectable signal. This is an explosion of probability and quantum mechanics playing out in ultra-slow motion across the entire observable universe. However, the path of frontier science is never straightforward, and the 3.5 keV line remains a subject of intense debate and scrutiny. The signal is incredibly faint, sitting right at the edge of what our current X-ray telescopes can reliably detect. Some subsequent observations have failed to find the line in places where it should be, while others have confirmed it. Skeptics have proposed more conventional, if still exotic, astrophysical explanations. Could it be the signature of complex plasma physics involving sulfur or potassium ions? These are heavy elements that, when in a highly charged state within the hot gas of galaxy clusters, can emit X-rays at or very near this energy. The problem is that to produce the observed signal, you would need vast amounts of these ions moving in just the right way, a scenario that some physicists find just as unlikely as the dark matter decay hypothesis. This ongoing controversy is in many ways the entire point. The hunt for the origin of the 3.5 keV line is a beautiful example of how modern science operates at the very limits of detection and theory. It's a high-stakes detective story where the clue is a minuscule bump on a graph. Proving it is dark matter would be one of the most significant discoveries in the history of physics, finally giving a name and a face to the 85% of the universe's matter that has eluded us for a century. It would open a direct window into the particle nature of the dark sector, allowing us to finally move from knowing dark matter exists to understanding what it is. The potential for a universe filled with decaying sterile neutrinos would reshape our understanding of cosmic evolution, from the formation of the first galaxies to the ultimate fate of all things. Yet, even if the line eventually fades away under more precise observations and is explained by mundane atomic processes, the search for it has pushed our instrumentation and our theoretical models to new heights. It reminds us that the most powerful explosions aren't always about raw power. Sometimes they are about paradigm-shifting potential hidden in the faintest whisper from the dark. Moving from the faint, ethereal whisper of a potential dark matter decay, we arrive at an event that provides some of the most compelling and visually stunning evidence for dark matter's existence, evidence carved out by a collision of almost unimaginable scale. At number 20, we encounter the Bullet Cluster, a system of two galaxy clusters that have slammed into one another in a cosmic impact that has unfolded over hundreds of millions of years. This is not a fiery blast of light and heat in the traditional sense, but a gravitational explosion, a slow-motion cataclysm whose aftermath reveals the hidden architecture of the universe itself. The bullet cluster, located about 3.7 billion light-years away, acts as a perfect natural laboratory, a place where the fundamental components of reality, stars, hot gas, and dark matter, have been violently and visibly separated by the forces of a colossal impact. To understand what happened here, imagine two vast swarms of bees, each containing billions of individuals, flying directly toward each other at millions of miles per hour. Now replace each bee with an entire galaxy and fill the space between them with an incredibly thin but immensely hot fog of gas. This is the scene of the collision. When these two clusters met, the individual galaxies, which are mostly empty space, passed right through one another with virtually no direct collisions, like two swarms of bees harmlessly intermingling. The truly massive component of the clusters, however, was not the galaxies themselves, but the enormous clouds of superheated plasma that filled the space between them. This gas, which accounts for the vast majority of the normal baryonic matter in a cluster, is so hot that it glows brilliantly in X-rays. When the clusters collided, this gas acted like a real, tangible substance. The clouds of plasma from each cluster smacked into each other, creating immense friction and pressure, and were dramatically slowed down and heated to even more extreme temperatures. They got stuck in the middle of the collision. This is where the story takes its revolutionary turn. While the normal matter, the X-ray emitting gas, was piling up and slowing down at the center of the impact, something else kept right on going. Astronomers mapped the total mass distribution of the bullet cluster, not by looking at the gas or the stars, but by using a technique called gravitational lensing. The immense collective gravity of the entire cluster acts like a lens, bending and distorting the light from even more distant galaxies behind it. By meticulously measuring this distortion, scientists can create a map of where all the mass in the cluster is located, regardless of whether it emits any light. The result was staggering. The gravitational lensing map revealed that the bulk of the mass in the bullet cluster is not located where the hot gas is trapped. Instead, two large, separate blobs of mass had sailed clear through the collision zone, accompanying the galaxies that had also passed through unimpeded. This mass, which does not interact with light or with itself through any force except gravity, had simply passed through the entire messy collision as if it weren't even there. The conclusion is inescapable. The majority of the matter in the universe is dark matter. The visible galaxies and the hot X-ray gas constitute only a small fraction of the total substance. The bullet cluster provides a direct, observational proof that dark matter is real, and that it is fundamentally different from the ordinary atoms that make up our bodies, our planet, and all the stars we see. It behaves as a collisionless fluid, its particles interacting so weakly with everything, including each other, that they were unaffected by the titanic collision that so dramatically impeded the normal matter. The separation between the pink clouds of hot gas seen in X-rays and the blue contours of total mass mapped by gravitational lensing is the smoking gun. It is the definitive signature of dark matter's ghostly nature, captured in a single, breathtaking astronomical image. The explosive nature of this event is written in the gas itself. The name bullet cluster comes from the distinct bullet-shaped shock wave visible in the X-ray data. This is the leading edge of one cluster's gas cloud, plowing into the gas of the other cluster like a projectile. The energy required to create such a sharply defined shock front in a cloud of gas that is larger than our entire Milky Way galaxy is almost beyond calculation. It is the aftermath of a blast wave on a truly intergalactic scale, a testament to the immense kinetic energy released when two of the largest gravitationally bound structures in the universe slammed together. This isn't an explosion that lasted for seconds or days. It is a continuous, billion-year-long release of gravitational energy that is still echoing through that region of space. The bullet cluster, therefore, stands as one of the most powerful arguments in modern cosmology. It is an explosion that didn't just release energy, but one that revealed a fundamental truth. proving that most of the cosmic landscape is built from a mysterious, invisible substance that shapes everything from the fate of galaxies to the ultimate destiny of the cosmos. At number 21, we must step back from individual cataclysms and confront the origin of all things, the event that set the cosmic stage for every explosion that would follow. This is the grand progenitor of power, the Big Bang itself, but it's crucial to move beyond a common misconception. This was not a conventional explosion in space, like a bomb going off in a pre-existing void. Instead, think of it as the rapid, dramatic emergence of space itself, along with time and all the energy and matter in the universe, from an initial state of near infinite density and temperature. In the earliest moments, the entire observable universe, everything we can possibly see today, was compressed into a volume smaller than a single atom. Then it began to expand and cool at an unimaginable rate, a process of cosmic inflation that set the fundamental rules for everything that was to come. This initial expansion is the ultimate explosion, not of material flying through space, but of space itself stretching and growing, carrying matter along with it. The most profound evidence for this event isn't a distant echo we have to strain to hear. It's all around us, a faint, cold whisper that fills every cubic centimeter of the cosmos. This is the cosmic microwave background radiation, the afterglow of the Big Bang. For the first several 100,000 years after the initial expansion, the universe was far too hot and dense for atoms to form. It was an opaque, searing fog of plasma, a soup of particles and light where photons couldn't travel far without constantly colliding with free electrons. But as the expansion continued, the universe cooled enough for a pivotal transition. Electrons could finally combine with protons to form the first neutral hydrogen atoms. In that moment, which astronomers call recombination, the cosmic fog lifted. The photons which had been trapped were suddenly set free to travel across the universe. That first flash of liberated light is what we detect today as the cosmic microwave background. It has been traveling for almost 13.8 billion years, and the expansion of the universe has stretched its once energetic waves into the microwave part of the spectrum, cooling it to just 2.7 degrees above absolute zero. When you see the static snow on an old, untuned analog television, roughly 1% of that signal is this primordial light, the oldest snapshot we will ever have of our universe, captured when it was a mere infant. This ancient afterglow is far more than a uniform blanket of cold radiation. It is a detailed cosmic blueprint. When scientists map the cosmic microwave background with exquisitely sensitive instruments like the Planck satellite, they find incredibly tiny fluctuations in its temperature variations of mere millionths of a degree. These minute ripples are the fossilized imprints of the quantum fluctuations that existed in the universe's very first instant. They are the seeds of all future structure. The slightly denser regions in this primordial map had slightly stronger gravity, which slowly, over billions of years, pulled in more and more matter from their surroundings. These overdensities were the gravitational wells that would eventually grow into the first stars, the first galaxies, the vast clusters of galaxies, and the immense cosmic web of filaments and voids that defines the large-scale structure of our universe today. Every galaxy, every star, every planet, and by extension, every one of the spectacular explosions on this list owes its ultimate origin to these faint patterns in the first light. This foundational explosion is unique in that its power was not purely destructive but profoundly creative. The energy released in the Big Bang was not merely dispersed, it was converted and woven into the fabric of the cosmos. The initial expansion forged the lightest elements, hydrogen, helium, and trace amounts of lithium, in a process known as Big Bang nucleosynthesis. This provided the raw fuel for the first generation of stars. The gravitational potential seeded by the density fluctuations provided the architecture for those stars to gather and ignite. Without this initial, universe-defining event, there would be no galaxies to host supernova, no massive stars to collapse into black holes, and no neutron stars to spiral together in Kilonova. The Big Bang is the ultimate source, the singular, unimaginably powerful genesis event that set in motion the entire cosmic cycle of birth, life, and explosive death. It is the explosion against which all others are measured, not for its flash, but for its enduring legacy, the creation of a dynamic, structured, and evolving universe capable of producing the very fireworks we have been counting down. Right when we thought we had stellar explosions neatly categorized, the cosmos delivered a spectacular surprise that forced us to rewrite the textbooks. At number 22, we encounter an event so peculiar it was nicknamed the Champagne Supernova, the brilliant and baffling SN 2003FG. This wasn't just another stellar detonation, it was a Type Ia supernova, a class astronomers rely on as cosmic yardsticks to measure the vast distances of the universe. But this particular yardstick was broken, or at least it was telling us a measurement that, according to all our established rules, was fundamentally impossible. To understand why this explosion was so revolutionary, you first have to understand the beautiful, predictable simplicity of a standard Type Ia supernova. It begins with a white dwarf, the Earth-sized, super-dense cinder of a star like our Sun. This stellar ember is typically stable, but if it has a companion star in a binary system, it can begin to siphon material away from its neighbor. As the white dwarf greedily accumulates this hydrogen and helium onto its surface, its mass gradually increases. There is a strict, fundamental limit to how heavy a white dwarf can become, a boundary set by quantum mechanics known as the Chandrasekhar limit, which is about 1.4 times the mass of our Sun. At this precise tipping point, the inward crush of gravity overwhelms the quantum pressure that was supporting the dwarf. The core becomes so hot and dense that it ignites a runaway nuclear fusion reaction, a titanic bomb that tears the entire white dwarf apart in a matter of seconds. Because this explosion always happens at the same mass threshold, it always releases roughly the same amount of energy, shining with a predictable peak luminosity. This incredible consistency is what makes Type Ia supernova standard candles cosmic lighthouses of known brightness that allow us to gauge the scale of the universe itself. It was by observing these very explosions that astronomers discovered the universe's expansion is accelerating, leading to the Nobel Prize-winning discovery of dark energy. SN 2003FG shattered this elegant model. When its light was analyzed, astronomers immediately realized it was far too bright. Its peak luminosity was significantly higher than any standard Chandrasekhar limit explosion could possibly produce. The data pointed to an unavoidable and, at the time, heretical conclusion. The white dwarf that exploded must have been significantly more massive than the 1.4 solar mass limit before it detonated. This was like a scientist declaring they had found a square circle. It simply wasn't supposed to happen. The Chandrasekhar limit wasn't just a guideline, it was a fundamental law of physics for degenerate matter. A white dwarf exceeding it should have collapsed directly into a neutron star, not exploded. So how could this super Chandrasekhar supernova exist? The hunt for an explanation led to several fascinating and exotic theories. One compelling idea involved the role of rapid rotation. Perhaps the white dwarf was spinning at a tremendous velocity. The centrifugal force from this spin could have provided extra outward pressure, effectively propping up the star and allowing it to accumulate more mass, perhaps up to 1.8 solar masses, before finally succumbing to instability and exploding. Another, more dramatic hypothesis suggested this wasn't a simple case of accretion from a companion. Instead, it could have been the result of two white dwarfs merging. In this violent scenario, the two ultra-dense stellar corpses would spiral together and coalesce, their combined mass easily exceeding the Chandrasekhar limit and triggering an almost instantaneous and far more powerful thermonuclear conflagration. A third possibility involved an incredibly strong magnetic field within the white dwarf. The pressure from this internal magnetism could have provided the additional support needed to sustain a super-Chandrasekhar mass, creating a denser, hotter bomb that would yield a brighter flash when it finally went off. The implications of SN 2003 FG ripple far beyond a single, overly bright supernova. This event exposed a critical flaw in our most trusted tools for cosmic cartography. If Type Ia supernova are not all perfectly standard, if some are inherently brighter because they come from more massive progenitors, then using them to measure the universe is like using a set of rulers that are all slightly different lengths. A miscalibration in our standard candles could throw off our measurements of cosmic distances, and by extension, our understanding of dark energy and the ultimate fate of the cosmos. The Champagne supernova was a thrilling and humbling discovery. It served as a sharp reminder that the universe is messier and more inventive than our cleanest theories, and that even our most reliable cosmic landmarks can sometimes turn out to be brilliant, beautiful, and utterly confounding outliers. Just when we think we have witnessed every form a cosmic explosion can take, the universe unveils a phenomenon where the cataclysm itself is invisible. A silent burst of pure gravity whose only evidence is a single speeding survivor. Claiming the number 23 spot is not a flash of light or a cloud of expanding debris, but a stellar cannonball known as the hypervelocity star SDSS J090745.0 plus 24507. This star isn't exploding in the traditional sense. It is the product of an explosion, a piece of stellar shrapnel from a gravitational detonation that occurred at the very heart of our galaxy. Hurtling through the Milky Way's halo at a velocity exceeding 1,500 kilometers per second, that's over 2 million miles per hour, this star is moving so fast that the galaxy's collective gravity cannot hold it. It is on a one-way trip into the emptiness of intergalactic space, a permanent exile set in motion by one of the most powerful engines in the cosmos. The story of this stellar fugitive begins with a cosmic dance that ended in a violent divorce. The leading theory, known as the Hill's mechanism, paints a dramatic picture. Imagine a pair of stars, a binary system, orbiting one another in a stable, long-term relationship as they journey through the galaxy. Over millions of years, their path slowly drifts, eventually carrying them into the densely packed and perilous environment of the galactic center, the domain of Sagittarius, a star, our supermassive black hole. As the binary system swings close to this gravitational monster, the immense tidal forces overwhelm the mutual gravity that binds the two stars together. The black hole's pull is vastly stronger on the star that is momentarily closer to it. In a fleeting, violent gravitational encounter, the binary bond is shattered. One of the stars is captured by the black hole, thrown into a tight, chaotic orbit from which it may never escape. The other, like a stone from a slingshot, is given an immense kick of velocity, flung away on a hyperbolic trajectory that will eject it from the galaxy entirely. This is not an explosion of fire and fusion, but an explosion of gravity and motion, a three-body interaction where the black hole acts as the trigger. The energy imparted to this star is almost beyond belief. To be flung free of the Milky Way, a star must achieve what is known as escape velocity, overcoming the combined gravitational pull of 200 billion stars, all the gas, and the immense, unseen halo of dark matter. The force required to accelerate a sun-sized object to such a speed is equivalent to the energy released by a supernova, but here it is focused into a single, precise gravitational kick. This process does more than just create a runaway star. It serves as a direct probe of the environment at our galactic core. The very existence of SDSS J090745.0 plus 24507 confirms that the supermassive black hole is not just a passive presence, but an active and dynamic force that can drastically reshape its surroundings, violently disrupting stellar systems and launching stars on incredible journeys. It is a celestial particle accelerator operating on a staggering scale. This lone star's epic voyage offers a unique and poignant perspective on the galaxy. As it travels, it carries with it the chemical signature of its birthplace in the galactic center, a region that is otherwise incredibly difficult to study in detail due to obscuring clouds of dust. By analyzing its light, astronomers can learn about the composition and conditions in the very heart of the Milky Way. Its trajectory is a permanent record of that ancient, catastrophic encounter, a frozen moment of gravitational physics that happened millions of years ago. We are not witnessing the event itself, but its long-term consequence: a solitary sun sailing into the void, a silent testament to the fact that some of the universe's most powerful explosions leave behind no expanding fireball, only a receding streak of light, a ghost from a gravitational cataclysm. But just when we thought our catalogues of cosmic violence were nearly complete, the universe delivered a stark reminder that it is still capable of producing events that dwarf our grandest expectations. At number 24, we have an explosion so monumentally powerful that it earned the instant and unambiguous nickname the Boat, the brightest of all time. This is GRB 221009A, a gamma-ray burst detected on the 9th of October 2022 that didn't just break records, it demolished them, resetting our entire scale for what is possible. The numbers associated with this event are simply staggering. It originated from a galaxy nearly 2 billion light-years away, a significant cosmic distance that should have rendered it a faint, difficult-to-study object. Instead, its intensity was so overwhelming that it completely saturated the gamma-ray detectors on NASA's Fermi Gamma-Ray Space Telescope and the Neil Gehrels Swift Observatory. Imagine a sensor designed to measure the light of car headlights being suddenly blinded by a nuclear explosion at point-blank range. That was the effect this single burst of radiation had on our most advanced instruments. Initial calculations suggest that for those few, breathtaking seconds, the boat was about 70 times brighter than any gamma-ray burst we had ever seen before. The energy it released in gamma rays alone, in just a minute or so, was more than our Sun will emit over its entire 10-billion-year lifetime. This was not merely a new champion, it was an event from an entirely different league of cosmic power. The sheer luminosity of this burst poses an immediate and profound question. What kind of cosmic engine could possibly generate such an unfathomable torrent of energy? The evidence strongly points towards the collapse of a truly colossal star, a stellar behemoth in a class of its own. This was almost certainly a long-duration gamma-ray burst, the death cry of a rapidly spinning Wolf-Rayet star whose core had exhausted its nuclear fuel. In its final moments, the star's core collapsed directly into a newborn black hole. As we've seen in other hypernova, this collapse triggers the formation of a superheated accretion disk around the black hole, fueling the launch of ultra-relativistic jets. What made the boat unique was the phenomenal efficiency and raw power of this process. The jet must have been exceptionally narrow and focused, carrying an almost unimaginable amount of energy, and crucially, it was pointed with near-perfect precision directly at our solar system. We were gifted, or perhaps subjected to, a perfect, head-on view down the barrel of the most powerful cannon ever witnessed, a focused beam of high-energy particles and radiation that had been traveling through space for almost 2 billion years just to deliver its message. But the initial gamma-ray flash, for all its record-shattering intensity, was only the opening salvo. The true legacy of the boat has been written in its spectacularly long-lasting and luminous afterglow. For weeks and months after the initial burst faded, the event continued to shine brilliantly across the entire electromagnetic spectrum. Ground-based optical telescopes watched it brighten to become a pinprick of light visible in amateur telescopes, a fading ember from a stellar catastrophe. Radio observatories tracked its evolving signature for over a year, while the Chandra X-ray Observatory continued to detect its high-energy echo long after the initial excitement had passed. This persistent afterglow is caused by the jet's interaction with the surrounding interstellar material. As the jet plows into the gas and dust that was shed by the star in its final millennia, it creates a series of external shock waves. These shocks accelerate particles to near light speed and generate the sustained emission we observe. The exceptional brightness and longevity of the boat afterglow suggest it was expanding into an unusually dense circumstellar environment, a testament to the violent and messy final chapter in the life of its progenitor star. The detection of GRB 221009 also provided a fascinating and slightly alarming lesson in our own cosmic context. While 2 billion light-years is a safe distance preventing any harm to Earth, the burst was still powerful enough to have a measurable effect on our planet's upper atmosphere. The wave of gamma rays ionized atoms in our ionosphere, causing a sudden and strong disturbance in long-wavelength radio communications. It even created a significant spike in the Schumann resonances, the natural electromagnetic frequencies that resonate in the cavity between the Earth's surface and the ionosphere. This served as a humbling reminder that even events occurring in a faraway galaxy can reach out and gently, yet perceptibly, touch our world. The boat was a wake-up call, demonstrating that the universe is not only more violent than we imagine, but sometimes more violent than we can imagine, and it can send its calling card directly to our doorstep. The discovery of this singular event so recently, in an era when we thought we had a good handle on the extremes of cosmic explosions, is perhaps its most exciting aspect. It proves that our census of the universe's most energetic phenomena is still incomplete. There are still mysteries lurking in the darkness, monsters waiting to be seen. The boat showed us that the upper limits of stellar death are higher than our models had predicted, challenging theorists to refine their understanding of jet formation, black hole birth, and the ultimate power output of collapsing stars. It stands as a brilliant, humbling, and exhilarating data point, a recent and spectacular testament to the fact that the cosmos always holds a few more surprises in reserve, ready to shatter our records and expand our horizons when we least expect it. And so we arrive at the final entry on our list, a cataclysm so immense it encompasses all of reality, a finale that is not a single, fleeting event but the ultimate fate of the cosmos itself. This is not an explosion we can point a telescope toward or capture with a detector. It is a slow, inexorable process playing out over timescales that dwarf the entire history of the universe to date. We are speaking of the theoretical end of everything, the final dissipation of all energy and structure. While it lacks the instantaneous fury of a supernova, this grand finale represents the ultimate expression of cosmic power, the final, drawn-out breath of a universe that has been exploding, expanding, and evolving for billions of years. The story of cosmic violence, it seems, concludes not with a bang, but with a fade to black, or perhaps with one last, unimaginable collapse. The prevailing and most widely accepted model for our universe's end is known as the heat death or the Big Freeze. Picture a universe that continues to expand as ours is, driven by the mysterious force of dark energy. Over trillions upon trillions of years, this expansion slowly but surely pulls the cosmos apart. Galaxies first recede from one another, disappearing over the cosmic horizon until every galaxy group is isolated in its own immense, expanding void. Within those galaxies, stars will continue to form for a time, but eventually the raw material for new stars, the great clouds of interstellar gas and dust, will be exhausted. The last generation of stars will flicker out, their nuclear furnaces cold. Some will end as white dwarfs, cold, dark crystals of carbon and oxygen. Others, more massive, will become neutron stars or black holes. And then, over almost incomprehensible eons, even these remnants are not eternal. Through a quantum mechanical process known as Hawking radiation, black holes will slowly evaporate, releasing their mass back into the universe as a faint mist of particles. In the final state of the heat death, the universe reaches a condition of maximum entropy. It is a thin, uniform, and frigid soup of subatomic particles and radiation, spread so thinly that temperatures approach absolute zero. No energy gradients remain, no hot spots or cold spots, no structures of any kind. It is a state of perfect equilibrium stillness. The ultimate explosion here is not one of release, but of dissipation. The final, complete dispersal of all the energy that was unleashed in the Big Bang, now spread so thin it can no longer do any work. It is the universe's energy, once concentrated enough to forge galaxies and stars, finally spent. But the heat death is not the only possible finale. Another, more dramatic and violent scenario hinges on the precise nature of the dark energy that is accelerating the universe's expansion. This is the theory of the Big Rip. What if dark energy is not constant but grows stronger over time? In this model, the repulsive force driving the expansion doesn't just push galaxies apart. It eventually overcomes all other forces in the universe. First, the acceleration would tear apart galaxy clusters, then individual galaxies. As the force intensifies, it would start to rip apart stars and planets within those galaxies. In the final, horrifying moments, perhaps in the last half hour before the end, the escalating repulsion would overcome the gravitational and electromagnetic forces holding planets and stars together. The Earth would be violently shredded. In the last instant, even atomic nuclei would be torn apart, unable to withstand the overwhelming pressure of space itself stretching at an infinite rate. The universe would end not in a cold whimper, but in a true, fundamental explosion, a moment when the very fabric of reality is ripped asunder at every point. Every molecule, every atom, every fundamental particle would be flung apart from every other, forever isolated in an ever-expanding, featureless void. This is an explosion of spacetime itself, a final, singular event that annihilates all structure in one catastrophic, universe-wide moment. There is a third, and in some ways more symmetrical, possibility: the Big Crunch. This is the classic implosion, a reversal of the cosmic expansion we see today. For this to happen, the density of matter and energy in the universe would have to be sufficient to eventually overcome the outward push of dark energy. The expansion would slow, halt, and then reverse. Galaxies would begin rushing back toward one another. The universe would contract slowly at first, and then with increasing ferocity. The cosmic background radiation, now a cold whisper, would heat up as space compresses, first becoming a warm glow, then a searing heat. As the contraction accelerates, galaxies would merge and collide in a universe-spanning firestorm. The sky would grow brighter and hotter until individual stars can no longer be distinguished. Eventually, all matter and energy would be compressed into an infernally hot, dense state, a singularity mirroring the one from which the universe was born. In this scenario, the ultimate explosion is actually an implosion, a collapse back into the primordial seed from which everything began. Some theories even suggest this could be a cyclical process, a big bounce where the universe undergoes an infinite series of expansions and contractions, a perpetual cycle of cosmic death and rebirth. Choosing between these fates is one of the ultimate goals of modern cosmology. The answer lies in precise measurements of the universe's expansion rate, the density of matter, and the true nature of dark energy. Every distant supernova we map, every galaxy survey we conduct, and every analysis of the cosmic microwave background brings us closer to knowing our ultimate destination. Whether it is a frozen silence, a catastrophic rift, or a fiery reunion, this final act brings a profound, philosophical closure to our journey through the universe's most powerful events. From the brilliant, localized death of a single star to the slow, inexorable fading of all starlight, the cosmos demonstrates that power can be both instantaneous and eternal, both creative and destructive. Our tour of these 25 explosions, from the nearby to the theoretical, reveals a universe that is fundamentally dynamic, a place where violence is not merely an accident, but a primary engine of change, complexity, and perhaps in the end of final, eternal stillness. The story of cosmic power is the story of everything, and it is a narrative that is still being written, with its final chapter waiting in the deep, dark future. As our journey across the cosmos draws to a close, we are left humbled by the sheer spectrum of violence we have witnessed. From the silent, graceful ballet of merging neutron stars forging gold in their wake, to the focused, relativistic fury of galactic jets that can sterilize entire swaths of space, the universe operates on a scale of power that defies human intuition. We have stood as spectators to the final, brilliant moments of massive stars, seen the ghostly echoes of supernova remnants expanding for millennia, and even traced our own existence back to the primordial explosion of the Big Bang itself, the ultimate creative event from which all others flow. This tour has taken us from our own solar backyard, where our sun can unleash planet-altering superflares, to the very edge of time, observing gamma-ray bursts from the universe's infancy. Each entry on this list is a stark reminder that the tranquil night sky is a grand illusion, masking a reality of continuous, breathtaking cataclysm. Yet, in every one of these events, we find a profound and beautiful paradox. Destruction and creation are two sides of the same cosmic coin. The supernova that tears a star apart is the very same event that scatters the essential elements of life. The oxygen we breathe, the carbon in our cells, the iron in our blood across the interstellar medium. The spectacular collision of neutron stars, a kilonova, is the universe's primary forge for heavy elements like gold, platinum, and uranium. Even the supermassive black hole at the heart of a galaxy, with its jets that can quench star formation, also plays a role in regulating galactic growth, preventing runaway consumption and sculpting the majestic spirals and ellipticals we see today. These explosions are not merely endpoints, they are catalysts. They are the engines of cosmic recycling, the crucibles in which the raw materials for new stars, planets, and potential life are minted. Without this constant cycle of violent death and rebirth, the universe would be a sterile place of hydrogen and helium, and we simply would not be here to ponder it. The story of cosmic explosions is therefore also our own story. Every atom in our bodies, every molecule on our planet, was once forged in the heart of a long-dead star and blasted across the galaxy by one of these magnificent detonations. We are quite literally stardust that has coalesced to contemplate its own origins. This connection transforms these distant, terrifying events from abstract phenomena into a deeply personal part of our heritage. They are the violent, chaotic, and necessary processes that carved out a niche for complexity to arise in an otherwise simple universe, ultimately allowing for planets, life, and consciousness to emerge. The cosmos is a place of infinite wonder and relentless power, and our exploration of it has only just begun. We would love to hear which of these titanic events left you the most awestruck. Was it the sheer, focused power of the boat gamma-ray burst, the ancient, echoing violence of the Vela supernova remnant, or the creative destruction of the kilonova that gave us the very elements we treasure? Share your thoughts in the comments below. Let's continue this conversation about the universe's most incredible displays of power. If you enjoyed this journey to the edge of cosmic violence and back, be sure to subscribe and hit the notification bell. There are countless more mysteries waiting for us to uncover, from the nature of dark matter to the search for life beyond Earth. Thank you for joining us on this tour of the 25 most powerful explosions ever recorded, and we look forward to seeing you on our next adventure into the mysteries of the cosmos.